recording? Yes. Okay, so in presence and our guests in remote. Welcome to Piero again.
Thank you, everybody.
It is really a pleasure to welcome our colleague and friend Piero Isacchi for our INAF Observatory Abruzzo colloquium. Let me briefly introduce Piero. I think that everybody knows him, but anyway, some background. Piero got his PhD at the Department of Astronomy in 2000. Department of Astronomy of the University of Oulu, Finland, in 2017, with a thesis on the visible and near-infrared spectroscopy of Mercury and Venus, with the supervision on Jorn Helder. Most of his thesis actually was carried out, and the research was carried out as a junior scientist at the German Aerospace Center in Berlin, Germany. And he also visited the Brown University in Providence during the same period in Rhode Island, US. After his PhD, Piero joined the University of D'Annunzio, Chieti Pescara, in 2019, the Department of Engineering and Geology, for work on solar system landing sites identification and selection. Then in 2022, finally, Piero joined the crew of the Observatory of Abruzzo and working on different projects on solar system science and planetary sciences. And this afternoon, Piero will talk about the volcanism, active volcanism in Venus, scientific implications and future perspectives through the AVENGERS project. So, yes, the microphone is yours. Welcome again, and you have 45 minutes.
Okay. Thank you, everybody. Thank you to the online listeners. Thank you, everybody here at the observatory for being here. So I'm going to share now the screen and start the presentation. Okay. See if it's working. Okay. So the title of the web seminar today is Active Volcanism on Venus, Scientific Implications and Future Perspective through the project Analogs for Venus Geologically Recent Surfaces, so Project AVENGERS. So today I will just consider also the audience. I will try to basically introduce you to the world of Venus, which is actually a planet very similar to Earth for some aspects, but also very different for other aspects. And we will go through the past discoveries, the geological studies made on Venus, and then I will move slowly toward the most the hottest topic on Venus, which is actually active volcanism. So, yeah, this is Venus. Venus photographed on the left by the Pioneer Venus Orbiter in 1979 in ultraviolet light. And you can see that the first images of Venus were that of a very mysterious world, because we could just see this planet very similar in dimension to Earth, but we couldn't see the surface because of its cloud coverage, so its dense atmosphere. So we didn't know what was just on the surface at the beginning, and it was a mystery. And you can see then with on the right side, an image taken by the Magellan, the NASA Magellan mission. This is a color-coded topographic map of Venus, taken by the Magellan spacecraft. And you can see what is on the surface. But the point is that, okay, many missions have crossed Venus during the past, let's say, 50 years, even more actually. So starting from, the Pioneer was indeed the Pioneer mission that told us something about this planet, but the first missions to really analyze to overtake the cloud coverage and to reach the surface of Venus were the Venera and the Vega missions, so the Soviet missions. that between the 60s and the early 80s have analyzed and told us actually something about the surface of Venus. You can see, in fact, on the left side, some images taken by the Venera missions, and we will see later also a little bit more in detail. And then during the years, we have had the NASA Magellan mission, which has performed a complete full resolution mapping of the surface of Venus at relatively high resolution, 75 meters per pixel of the surface of Venus in the radar, because radar is the only way we can, let's say, overtake the cloud cover of Venus. And then in the more recent times, there have been other missions. The Cassini, Galileo, and the Messenger mission also has made some flybys on Venus. And especially the Venus Express is the ESA Venus Express is another mission that told us something about, let's say, the surface, because it was analyzing Venus in the infrared spectral band, which is something that we will say later on. And then the Akatsuki mission, the Japanese mission. So let's take a look at the surface of Venus. Okay, these are among the very few images that we have from the surface of Venus. You can see this is a color image up. You can see a color image as seen on the surface of Venus by the Venera 13, the Soviet Venera 13 lander. And you can see instead down another image taken by the lander with atmospheric effects removed. So yeah, okay. You can see here how Venus looks at a human eye. So basically, it's a desertic world. It's a volcanic world. You can see the extensive lava flows, and the Soviet landers which landed on Venus also told us about the composition of the surface of Venus, which is mainly basaltic. So it reminds actually the composition of terrestrial volcanoes like Hawaii, for example, Hawaiian volcanoes. The point is that what those landers found out, yes, it's that Venus is a hell. So Venus is often considered as the hellish twin sister of the planet Earth, because, yeah, it looks apparently very similar to our planet, because it shares with Earth dimensions, because basically Venus is almost as big as Earth. The mass of Venus is about 30% of the mass of the Earth. And it also has this very consistent atmosphere. But what actually the Soviet landers found on the surface is hell. 475 degrees Celsius degrees on the surface. So it's enough to cook a pizza, basically. And with 90 bars of atmospheric pressure. So the same, almost the same pressure that we could experience at about 1 kilometer in the water. So, and also sulfuric acid clouds that can cause actually acid rains that don't reach most likely the surface, but still it's a very hellish environment. We can see, however, this is the temperature and pressure profile. We can see how the situation changes as we move at higher altitudes. So about 50 kilometers of altitude, we have a very different situation. We have that the atmospheric pressure decreases up to 1 bar. So very similar to that of the Earth. And also the temperature is very like habitable temperature, 20 Celsius degrees. This is why some scientists, some studies have proposed that maybe some microbic life may exist in the clouds of Venus at this altitude, more or less. Also, recent studies have detected the possible presence, so it's not confirmed yet actually, but the possible presence of traces of phosphine, which on Earth it's basically a biosignature trace gas. So, so it's a biomarker on Earth, but we don't know on Venus, because on Venus, if it really exists, this gas, then it would be also related to maybe volcanic activity. We don't know. So its origin on Venus may be also abiotic. We don't know. But anyway, it's possible, and this is actually something that the future missions to Venus should analyze. So the possible presence of also life, let's say microbic life in the clouds, it's a possibility. Okay, so let's move a little bit to the past of Venus. So why we say that Venus is so similar to Earth? It's not only a matter of dimensions. It's also because it may have shared a very similar past compared to that of the Earth. Venus, as we can see here, billions of years ago, may have had oceans. We don't know, but it's a possibility. It's a possibility that should be explored by future missions. And so, if really Venus had oceans in the past, it was so similar to Earth, how it is possible that it became such a hell? Because the point is that Venus, basically, it's so hot not because of it's closer to the sun, but because basically the few radiation, the few solar radiation that reaches the surface of Venus cannot escape anymore, causing this so-called runaway greenhouse effect. So basically, yes, that's the mechanism that made Venus so hot, and especially that made Venus, the temperature of Venus so uniform around the whole planet. So because the temperature of Venus is very constant on the surface around the whole planet, and it only varies with the altitude. So if the oceans evaporated, why did this happen? This is something that the future missions should, this is actually a science question that the future missions should target. And so this topic opens up also to another scientific, very interesting target, that of the exoplanets. So Venus has been often compared to exoplanets. Actually, exoplanets have been compared to Venus. For example, let's take an example, the TRAPPIST-1 exoplanetary system. So this system is made of, as we know, of course, has been proposed by recent studies. It may be formed by 7 planets orbiting very near basically the major sun, let's say, of this system. And scientists have recently proposed that most of those 7 planets, or even all of them, may have evolved in a very similar way as Venus. So they may have had very similar conditions to that of the Earth at the beginning. So they may have had also water oceans billions of years ago, but they may have lost those water oceans to be replaced by a very dense atmosphere and very toxic environment. Of course, these are still ongoing studies, so these are, of course, just proposed research works, but it's also a possibility that we should explore. I mean, if Venus is so similar to exoplanets, so then we should see it can help us also to understand a little bit more of how basically the exoplanetary systems can evolve during the geologic time. So let's move a little bit from the atmosphere of Venus and the atmosphere-surface interactions to the interiors of Venus. So Venus, it is also different from Earth for another reason. Okay, this is Earth. We can see that volcanism on Earth is dominated by plate tectonics. So basically, actually, volcanism on Earth, it's a mix of 2 different types of volcanism that we call intraplate and interplate volcanism. So on Earth, we have both types, and it is sure on Earth that a lot of volcanoes are aligned along the margins of the plates. So because, of course, Earth is divided in plates, and a lot of volcanoes on Earth are basically aligned along these plate margins. And but we also have, like in Hawaii, for example, we also have what we call hotspot volcanoes, whose magma comes from really deep origin, from deep in the mantle. So okay, and we can see instead here basically what is the difference, the major difference between the models, at least, of volcanism on Earth and on Venus? Because Venus doesn't have evidence. We didn't find so far evidence for plate tectonics on Venus. So we do not see plates on Venus, which doesn't necessarily mean that there are no, or that haven't been in the past, but that's what we know, is that we don't see so far evidence of plate tectonics. So basically, volcanism on Venus, as you can see down to the right, should be driven by a mechanism more similar to those of Hawaiian volcanoes. So with magma coming from deep into the mantle, but there are no, basically, there are no movements of the crust. Because there are no movements of plates. And okay, and here we see the major difference between Earth and Venus. So volcanism on Earth and Venus. You can see, I will move with my mouse now. Okay, you can see on Earth up that many, these are terrestrial calderas. You can see that many calderas on Earth are basically aligned along the plate margins. So they have a non-random distribution. And instead on Venus, down, you can see how already at the human eye, the distribution looks definitely more randomic. So it's definitely random. And this is another reason why we say that basically volcanism on Venus is mainly Hawaiian, so it's hotspot-like, and it's not due to plate tectonics activity. Even if we cannot exclude that some areas may also have experienced some form of, let's say, subduction, which is the mechanism through when basically one plate goes under another one. So Venus is a planet which, let's move now to volcanic features in Venus, because Venus has a lot of, it's a volcanic planet, so it's made of volcanoes. And so some volcanoes on Venus are very similar to those on Earth. So they look really similar. They may be compared to shield volcanoes on Earth, but some are really specific of Venus. So for example, we have these funny features here named coronae. They are funny because actually we don't really see them on Earth. And features like these are named coronae because they remind the shape of a corona, from Latin, so crown. And they are basically a large central circular structure and surrounded by concentric fissures. So, and they basically form when the crust is raised by hot floating magma beneath the crust, and then it gets released when the magma basically cools down, and so forming this corona. And we can also see another evolution of coronae called arachnoids. Arachnoids are more complex features. They were called in this way by Soviet scientists because of their spider-like shape, let's say. They remind, in fact, the spider web. If we look at these features, they remind a little bit of the spider web. So, and they usually contain also central volcanic complex, let's say. And they have proposed that they may also remind the initial phase of formation of Venusian calderas, but the truth is that also those features are very mysterious, so we don't know how they can form, and that's why Venus is also a great mystery, because there are really volcanic features that for which we don't really know the formation. And instead, as I said before, there are volcanoes which are much more similar to basically to that of to terrestrial volcanoes. So, for example, we see here Mount Mons. Mount Mons is probably one of the most famous volcanoes of Venus. It is characterized by the presence of a large caldera about 30 kilometers across on its summit, so like many volcanoes on Earth. And Magellan radar detections proposed also, initially proposed in the past years, the possible occurrence of volcanic activity at this volcano. And also investigations performed by the Pioneer Venus probes proposed some changes in the variations in the concentration of the sulfur dioxide and also methane above this volcano, which may also kind of tell us something about the possible volcanic activity of this volcano. But yes, this is a very recent study by Eric and Hensley, just published 1 month ago on Science. And it's possible evidence, basically, this is the authors of this study found the variation in the shape and diameter of a volcanic vent that you can see here down. So this one and this one, you can see the change basically between the cycle 1 and cycle 2. So basically the Magellan radar instrument observed Venus in 2 different cycles, left looking and right looking. So in 2 different moments of time. And so in these 2 different moments of time, we have the authors of this article have noted this difference in the shape of this volcanic vent, which may be an evidence of active volcanic activity. Active volcanism, and so may also give us kind of very strong evidence of volcanic activity on Venus. They also proposed the occurrence of new flows in the second observation made by the radar instrument of the Magellan mission. So new flows also. And this volcanic vent is located very near Mount Mons. So this may be actually a further indication that Mount Mons, for example, is an active volcano of Venus. But there have been also other studies, and actually this is something that I am more focused on, also my research study. So landing site selection and analysis of potentially active volcanic areas of Venus. So Venus, let's say that the crust of Venus is relatively young. It's about 300 million years young, which is, in terms of geologic time, it's not really a lot. But there are areas of Venus that are pretty young, so that are younger than the rest of the surface. Those areas are called so-called topographic rises. So they are basically bulges, they are kind of resurgences of the surface. And they may be formed by magma, by plumes of magma, raising up to the surface and forming, these so-called rises. One of those is particularly interesting, and it's called Indre Regio, that based on the data we have so far, may be actually among the youngest between the young topographic crises. So if the topographic crisis with dashed red lines, actually these are the topographic crises. So if they are already very young, this region may be the youngest, or more or less among the youngest of Venus. Because its topography, it's very young, and also there is a big star in this region, which is called Hidden Mons. It's an active volcano that I've also been extensively studying in the last years with other colleagues. And so this volcano became a big star because recently the ESA Venus Express mission identified 1 micron anomalies, infrared anomalies over the top and distant flank of the volcano. So the anomalies are indicated by this red spot over the top of the volcano. So this red spot basically indicates younger materials. Of course, younger materials over the top of a volcano means probably can imply at least the occurrence of recent volcanism. Why we use 1 micron emissivity anomalies on Venus? Because on Venus, this, let's say, the spectral band can tell us a lot about the oxidation of material. Because on Venus, we have very strong atmosphere surface interactions, let's say. So basically, materials, once erupted on Venus, so young lavas, once they erupt on the surface, they get very fast oxidated on the surface because of the thick atmosphere. It's interacting very fast with the surface. So there is this chemical so-called technically chemical weathering that really tends to oxidate material very fast. So very fast in terms of geological time. Previous studies from Smrekar et al. In 2010 proposed actually an age for the oxidation about 250,000 years. So basically saying that this red spot that we see here may be 250,000 years old, which is still like yesterday in terms of geological time. So saying 250,000 years ago, for geology, it's like saying present. This is it. So this is a detail of the red spot that we can see. It's a cooler image, of course. There is also the heat map and the radar. So you can see up the Magellan radar reflectivity map, and down you can see also the heat map overlapped over the Magellan reflectivity map. And this is actually something that I have been also working on, trying to identify location and extent of those lava flows. So basically, we saw this red spot, but we didn't know if the lava flows would actually come more from the top or from flank bands, basically flank eruptions. So we used, I speak plural because yeah, it was a group work. So we used the Magellan radar images at high resolution because yeah, we see that this red spot was very low resolution. Yeah, the red spot was very low resolution because the ESA Venus Express data were really low resolution. So we used the Magellan radar images at higher resolution to map the units, so the lava flow units of the volcano, and then with an emissivity modeling, we assigned basically hypothetic values of emissivity to each mapped lava flows, and reconstructing basically the modeling and reconstructing through the basically the minimum error, let's say, we reconstructed which scenario could better approximate the observation of the Venus Express spacecraft. And it turned out that the scenario that better approximates the observations was the scenario number 7, where we assigned high values of emissivity to the flank lava flows. So basically, according to this modeling, the flank lava flows would be responsible of the red spot, so the emissivity anomalies observed here, basically. We also made an independent stratigraphical mapping to see, basically, geologically, there are other methodologies to see what flows are younger and what flows are older, let's say. And it turned out also from this blind check, let's say, geological blind check, that the two observations were in agreement. So the emissivity modeling agreed also with the geological mapping in saying that the flank lava flows were basically the youngest ones and possibly responsible for this red spot, let's say. Yeah, you can see here the flank flows in detail, and you can see the red spot there. Okay, so you can see here instead a regional view of Olapakasma, which is basically a rift which interacts with this volcano Idun Mons, which is, by the way, Idun Mons is a volcano which reminds a little bit of shield volcanoes on Earth, let's say. So not really Hawaiian, but anyway, morphologically, yes, can remind a little bit of Hawaiian volcanoes. So in general, we have to say that morphology on Venus is very gentle. It's not like on Earth. We don't have really tall volcanoes on Venus. We have really generally more gentle physiography. So this is more basically could be due also to the very high atmospheric pressure and different surface conditions on Venus, of course. So we can see some geological interactions. So we can see how complicated it is actually to interpret the geology on Venus. And we can see that these volcanoes, as many other volcanoes, also has a strong interactions with rift zones. And it is very interesting to analyze these areas because some of these areas may be similar to other volcanoes on Earth or volcanic zones, like, for example, the East African Rift. which is an opening rift, and it could be also a comparable site. Another reason why this area is very young, I was saying that the Idun Mons is the major star of the area, but so the volcano. But there are other reasons why we say that this area is very young, and it's volcanically young, but also tectonically young. So when I speak about tectonics, I speak about fracturing of the surface. So basically on Venus, we have active volcanism, but we may also have contemporaneously fracturing. So maybe, who knows, also Venus quakes. So this is so we analyzed also an impact crater on the west side of Idun Mons, this small impact crater indicated by the black square, which also allowed us to basically let's say propose an age for the area. And it is interesting because we can see the fracture. So we identified, this is another article that I have led. And so basically there are fractures. We identified fractures entering, disrupting, let's say, the impact ejecta of this impact crater, so the ejecta of this impact crater. And we concluded that most likely tectonic activity, so the fracturing, started before this. Important to say that this impact crater is very young. So it's relatively young, it's very young. We could tell it based on radar observations and based also on the morphology of the crater. So the crater is very young, but despite this, yeah, we observed some fracturing entering basically even in the floor of the crater, as we can see, for example, here. As you can see, the white arrow. So this is a fracture entering in the floor of the crater. So this is a very recent crater, and imagine a fracture was disrupting its floor, which means that of course it postdated the formation of the crater. And so it means we concluded that most likely the fracturing started before the formation of the crater, but it continued after the formation of the crater, meaning that volcanism and fracturing, so volcanism and possible Venus quakes, why not, may alternate in time over these areas. And we can see also another evidence from another possible evidence from this image. We can see, for example, some lava flows indicated by these very bright areas here, because, okay, interpreting radar images, of course, it's different. It's not like observing, let's say, visible images, but we can see some lava flows here. We can see some lava flows here covering some fractures. So this is a fracture which is basically covered by this lava flow. And instead, for example, here where the white arrow is, we see instead a fracture disrupting the lava flow, which means that basically sometimes the fractures disrupt the lava flow, so they postdate the lava flow. Sometimes instead the fractures are covered, buried by the lava flow. So the lava flow, the volcanic activity basically comes later. So which means that the volcanic activity and tectonic activity, so fracturing, alternate in time, very closely in time. And so this is why, for example, it is very important to kind of connect the study of these areas, also to compare these areas to possible active areas on Earth, like the East African Rift, which is a very similar area on Earth. And another reason why, so before I was mentioning that oxidation on Venus acts very fast. And before I mentioned also that the red spot that we identified over this volcano may be 250,000 years old, which is still yesterday in terms of geological time. But there was a very recent study, and this is very interesting, that made by one of our collaborators, that they basically some igneous minerals and volcanic rocks were tested in the lab under Venus conditions of similar temperature, and to analyze basically the time of oxidation. So these materials were inserted in the lab unaltered, and then they observed how long the oxidation would take under Venus conditions. And they found out that actually under Venus conditions, the oxidation may occur much faster than previously thought. So not in the order of 250,000 years, but in the order of weeks to years life. So in the orders of a lifetime, which means this implies that the red spot we identified here maybe not, this red spot may be not 250,000 years old, maybe just some months to years at the time of the observation, of course, which was made in 2008. So, sorry, 2006, 7. So maybe just a few months to years old. And this is why it's very important to analyze these anomalies, 1 micron anomalies, because the 1 micron band, it's, I don't want to be now too specific, but the 1 micron band on Venus can tell us about, it's the most specific band for identifying this oxidation, let's say, because that's the range that tells us something, spectrally speaking. So we see why it is so important to analyze basically volcanoes on Venus, why volcanism is important on Venus, because it may help us reconstructing the geological history of this planet, but it can also help us to better understand the Earth. In fact, actually, something that I didn't mention at the beginning is that in planetary geology in general, it is very important to act always like compare. So comparing. A comparison, it's always fundamental. We have to compare features to understand better, of course, the planet where we live, but also to understand better the evolution of other planets and other solar systems. And for this reason, we are now starting a new project, the project which is also mentioned in the title, the project Analogs for Venus Geologically Recent Surfaces. So project AVENGERS, where we basically plan to build a database of terrestrial volcanoes, young active volcanoes on Earth, and to compare those volcanoes to possibly active volcanoes of Venus, to basically understand and to get also a better, understanding of the processes forming behind the formation of volcanoes on Earth, but also the processes behind the formation of volcanoes on Venus. Of course, it is very important to say that there is no perfect analog. So that's why we will need to build a database, because every volcano on Earth can share some similarities with volcanoes on Venus, but can be different for other reasons. So, for example, what we will do now, we are starting from Mount Etna. We can see two radar images here. On the left, you see Idun Mons, so the big star volcano that I showed you before. And on the right side, you can see instead a radar image of Sentinel-1 image of Mount Etna at the more or less the same resolution of the Magellan image, so 75 meters per pixel. Yeah, you can see, okay, the two volcanoes are a bit different in size, but they share, as we can see, okay, maybe it's a bit too bright. Let's see if I can, no. Okay, it's maybe not so visible, but you should trust me on my word that, yeah, there are basically multiple caldera collapses. So there are multiple calderas here on the top of Idun Mons. And you can see also that Mount Etna, for example, has a very similar top in this sense, that it is also characterized by these multiple calderas, even if the two volcanoes are genetically different. So because morphologically, as I said before, Idun Mons may be more similar to Hawaiian volcanoes. On the other hand, there are these top calderas which make it more similar to Mount Etna, which is a stratovolcano, which is actually a volcano which alternates very fluid eruptions to more explosive eruptions. So it's a mystery, of course, to understand also a little bit better the origin of hidden mounts, because we need more data to understand it. We also need gravity data. We need a lot of additional data to understand, but we can start by comparing. And so, for example, this is, we started also with a field trip. This is me with a colleague, a geochemist, Nicola Mari, retrieving samples from Mount Etna that then we analyzed in the lab. So I can show you. I don't know if you can. This is us collecting samples, so you can see also us while working. And this is basically this is how geologists work. Yes, because yeah, there is science, but there is also field trips to make. And so after retrieving these samples, we started to analyze, and this is actually what we are starting to do in this project. So we are analyzing the spectra, the 1 micron band of these samples, and actually in a bit wider range. And we started to analyze weather spectra that show basically a concave curve around. So you can see the unweathered spectra. So this is the age scale, and you can see the blue spectra indicate younger materials, basically. Unaltered materials, and yes. And you can see that on younger lava flow samples, you can see basically this concavity, and you can see also this curve here. So you can see this absorption band visible near 1 micron. But for older samples, so for older ages, let's say, you can see that the concavity is lost. So we lose this absorption band for older materials, let's say, for older lava flow samples, because of the oxidation. So the oxidation is basically let's say, the mechanism through which we lose the absorption band. And that's why it is very important to analyze the spectra in this particular range. Okay, so we can see also some of the samples. Okay, down to the right. You can see me up to the right, and you can see also one sample that we have retrieved from Mount Etna, and we are continuing our analysis to include more and more volcanoes. So Mount Etna is only the first one. We chose Mount Etna also not only because it offers the opportunity to analyze more different, let's say, different lavas, because as I said, we have fluid lavas, but we also have more explosive products, volcanic products. So we can analyze different type of volcanism on Mount Etna. But one other reason is that Mount Etna is also very easily accessible. So we want to go there and retrieve samples as we did. So it is very important. We will also keep going to analyze other volcanoes. Of course, we want to analyze Hawaiian volcanoes, and there are other possible volcanoes that we want to analyze, all active ones, of course. We want active volcanoes. And yeah, so this is the beginning of the project, of course. We are still in embryonic phase, and yeah, so this is it. I think, yes, it's over. So thank you very much. I think we are more or less.
Perfect time. That's it. Actually,
5 minutes. So if there are questions here in the room or people, so we have questions from remote. Okay. And people who have questions, okay, let's start with data.
In Houston, the lab of LPI, the Lunar and Planetary Institute, yes. But we can also use, we are also planning to use the other labs at the Johnson Space Center. Yeah.
People online, if you have questions, please unmute yourself.
Can I ask something? I'm curious about, there are so many missions from business approach.
Yes. I did not mention, in fact, because there are so many missions.
Yeah, you mentioned that, the instruments you've focalized are mostly imaging.
Yes.
But I guess that's not the only kind of, or do we only have those kind of? I mean, and what? So do we have also other kind of analysis?
Yeah, we have
in the future. What are the perspectives in terms of observations? And
Yes.
stuff?
So.
Okay,
so it is. Thanks a lot for the question, first of all, because in fact, I didn't mention. I forgot to mention that there are really many missions that have been selected to Venus. Venus is a planet that has been forgotten for too long, for really many years. After the Magellan mission, basically we only had a couple of other missions: the Akatsuki, the Venus Express, in the early 2000s, so, but nothing more. And now instead we have actually two NASA missions selected for launch, so the Veritas and Da Vinci mission. And I'm here to work actually with Gaetano Di Achille. We are collaborating we are providing geologic support to the gravity experiment of the Veritas mission. So not imaging data, but of course they can be also translated to images, but mainly gravity data that we will retrieve. And then there are also other missions. So there is the ESA Envision mission, which also mounts an Italian instrument from the University of Trento, a radar sounder, basically ground penetrating radar. And then we have an Indian mission, the Shukrayan-1, and the Roscosmos Russian Venera-D mission, which is basically a continuation of the Soviet missions, which did also bring a lander again to the surface of Venus. So we have a lot of data. Yeah, many of them can be anyway translated to kind of images or kind of GIS or geographical information system layers that we can visually interpret somehow, because this is how we, at least we geologists, like to work. So visually seeing anomaly variations, so heterogeneities and everything. So we like to anyway have layers. We have visual. So you mean what kind of images actually?
No.
Yeah. Okay. We have infrared spectrometers. We have actually, for example, the Venus Express, the instrument that found this red spot over the top of Idul Mons, of that volcano, was the infrared spectrometer called PIRTIS. And there have been also other spectrometers over the Akatsuki mission, and there will be also spectrometers over these other missions going to Venus in the next years. So we have spectrometers. We have, of course, we have also the gravity experiment. So we have instruments analyzing also the gravity of Venus. We will have also the radar. Of course, it's a major instrument for Venus. We have the new of the ground penetrating radar, and we have landers also. Again, as I said, landing on the surface, we take geochemical data directly from the surface. So I hope I'm not forgetting anything very important, but yes, we have a number of instruments.
Curiosity. So you do know that such kind of studies were done on a much larger scale for Mars. So how do the studies on volcanism on Mars helps for your study?
Well, comparative study can always help because, as I said before, we never have the perfect analog. So either we talk about terrestrial analog or a Martian analog for Venus. We never have the perfect analog. So that's why it's always important to analyze different in this case, since we are talking about volcanic activity, volcanism, it is important to analyze different volcanoes because each structure can tell you, each volcano can tell you something specific, you know. So that's why comparison is important, because you can find similarities, but you can also find differences that may help you. Sometimes, you know, differences can be also as important as the similarities to understand a particular scenario and the particular evolution of, in this case, for example, of volcanism on Earth, Venus, and Mars. If you now you mention also Mars. Now we are focusing on Earth because, you know, of course, we can go to these volcanoes, we can retrieve samples, we can analyze samples in the lab. So field trip in geology is always very, very important. So, for example, Mars, we can take advantage, of course, of the many missions that we have. So we have rovers which went to Mars, and they got actually incredible images from the surface, but still we cannot perform field trip, so which is geologically fundamental.
We have a question from Triana.
So thanks for the presentation. Is the project just for volcanoes? Is there a way to include craters? Mostly those that are formed because they explode in the atmosphere. So,
No, not directly in this project, because this project is majorly focused on volcanoes, so each type of volcanic structure. So impact craters anyway have a different origin, and they are very interesting, even if for Venus, maybe, let's say that Venus is less famous for impact cratering because the surface of Venus shows really few impact craters. For example, unlike what we see on the Moon or on Mercury, we see a lot of impact craters, and they are useful to date the surface. For Venus, impact craters are not really that useful, even if I showed before an exception, because we were very lucky to identify near the volcano, the possibly active volcano of Hidden Mons, a very young impact crater. But that's a kind of exception in this, because there are few impact craters. So, and as I said, most importantly, they have a different origin. So here we are focusing on volcanic activity, which is originated by the interiors. So that's why it's important to focus this.
From Gerald Tavana, do you think that our past and current models are being limited by low spatial resolution of data sets, leading to this interpretation?
Of course, of course. Actually, I have not here an image, but there is a very interesting image I have not included in this presentation, showing some small fields of cinder cones. So cinder cones on Earth are explosive, little explosive volcanoes. And we found similar features, also morphologically similar features on Venus, near these volcanoes, these Hidden Mons. And we don't know the origin of these features, but we saw that they are much larger on Venus just because of the limiting resolution. But we don't know, maybe we may also find other features, smaller ones, but we are limited by the resolution. So even if there are, we cannot see because we have only 75 meters limit of resolution on Venus, so we don't know. And so, of course, some of our interpretation can be surely limited by the actual resolution of the data. That's why we urgently need the future missions, because yes, we need to improve the resolution and we need actually even a larger data set.
Many fields of us. Okay, if there's no comment or questions, let's thank again Piero.
Thank you very much, everybody.
And for those who are asking the webinar and the presentation, both will be available on YouTube and on our website.
Okay.
So in that it's just
Okay.
We'll meet in a couple of weeks for our next meeting. Ciao. That's it. And next webinar will be in the morning. And
Ciao. Grazie.
Ciao, grazie.
Oh, ci sta.